Topic of the day is integrated rate laws. We like to integrate our rate laws so that we have a means to determine the values of variables with respect to concentration versus time. We're going to be primarily focused on zero, first, and second order reactions. It just so happens that what we see before us here is an integrated rate law for a first order reaction. And notice that it is in the form y equals mx plus b. This is very useful to us in order to explore that relationship of concentration versus time. This is a summary of the integrated rate laws for zero, first, and second order reactions, all of which are in the form y equals mx plus b. If it's a zero order reaction, notice that our y is simply the concentration of A, and we're plotting that against the variable of time. If it's a first order reaction, we have the natural log of A. Again, we can plot that against time. And then for a second order reaction, we have the inverse of the concentration. 1 over A can be plotted against our x variable of time. There's other things going on here as well. We have a slope that is determined by the value of K and may be positive or negative. But really, these are the basics. This is the heart of the matter for the integrated rate law. And we're going to take this now and we're going to use it for exploring how to solve a first order problem. Let's say we are converting cyclopropane to propene, and we know it's first order kinetics, and we're given a rate constant. That rate constant is given right here. The reaction is this, and we know it's first order with respect to cyclopropane. If we are told the initial concentration of cyclopropane was 0.25 molar, we can use our integrated rate law to find the concentration after 8.8 minutes. We can do other things as well. We could establish how long in minutes it would take for the concentration of cyclopropane to fall from 0.25 molar to 0.15 molar. And we could do yet another calculation and determine how long in minutes it would take to convert 74% of our starting material, again, cyclopropane. We're going to start with the solution to part A. Again, we're given that we're starting at an A sub 0, our initial concentration of 0.25 molar, and then ask for the concentration of A at time t, which is after 8.8 minutes have elapsed. So, you may have seen, it went by quickly, but you may have noticed that the values of K are given in seconds to the negative 1. So we must convert our 8.8 minutes to seconds first in order to be consistent with our units. That's simple enough to do. We simply convert 8.8 minutes to 528 seconds, and now we're really ready to deploy the integrated first order rate law. This is in the form that we see here, and we're going to simply plug in our numbers. The negative of the value for K, the time in seconds, and the natural log of our starting concentration. This means that the ln of A at time t is going to equal negative 1.74. Now we have to take the antilog in order to get our answer. We raise E to the negative 1.74, we get 0.18 molar. Notice, yes, our concentration has diminished. We could also just pause for a moment to think a little bit how the K is definitely going to affect how long it takes for a reactant to diminish. The values of K vary enormously by reaction. In this case, I wouldn't say this is an extremely fast reaction. It takes almost 9 minutes to get from 0.25 molar to 0.18 molar. This is a change, of course, but it's far from instantaneous, let's put it that way. Okay, so now what are we going to do? We are going to use first order integrated rate law again to determine the time required to diminish from 0.25 molar to 0.15 molar. In this case, we're given both concentrations. Clearly, this will allow us to solve for T. So if you think back a moment ago, given a certain amount of elapsed time, we were asked for a change in concentration. Now, given two different concentrations, we're going to look for the elapsed time. The equation can be rearranged to look like this. The ln of concentration of A at time 0 over concentration of A at time t equals kT. We plug in all our numbers, including K here, and we find that it takes 13 minutes to get from 0.25 to 0.15. If we do a common sense check on our answer, a moment ago we said it's close to 9 minutes to get from 0.25 to 0.18. Now we're seeing, okay, 0.25 to 0.15 is 13 minutes. Everything in our garden is working. Part C involves how long in minutes it will take to convert 74% of the starting material. We are trying to trip you up here because when we say converting 74% of the starting material, what we're really saying is that 26% is going to be left. In other words, we've taken away the 74% from the full 100% that we started with. We will again use this form of the integrated first order rate law, and we will convert to the fractional amounts of 1 and 0.26. This is just a little bit more convenient. When we plug in the numbers, it's the natural log of 0.26 over 1. This is equal to K times the time. We simply solve for the time. If we want to convert that to minutes, we certainly can because that's how it's actually asked in the question. And then we're done. Another use of the integrated rate laws is to determine the order of a given reactant from graphical data. Imagine you have run an experiment and you have kept meticulous records as to how concentration changes with time. In other words, you start out at time 0, you have a certain concentration, you let your reaction run, you could take the data every 10 seconds, every 50 seconds, whatever it is you determine works best for your reaction. And then you have a whole bunch of data. So you can use that data and you can plot it 3 different ways. You can simply plot the concentration of A against time. You could plot the concentration of the natural log against time, and you can plot the concentration of 1 over A versus time. To be very clear, you're taking the same data and you're replotting it with different variables for your concentration, A, ln of A, and 1 over A. Now, if your experiment has gone well, one of these plots will turn out to be linear. And the one that's linear in the form y equals mx plus b is going to tell you the order of your reactant. Curved lines tell you, it's not 0 order. No, it's not ln of A first order. Linear means, in this instance, second order. Let's look at all the possibilities in the next slide. In each of these cases, this is hard to read, unfortunately. This one is A versus time, zero order. This is ln of A versus time, first order. This is 1 over A versus time, second order. So in this instance, if this is how our data came out, this would be a zero order reaction. In other words, changing the concentration has no effect on the rate. In this instance here, it would be first order because the linear only occurs when we plot the natural log of concentration versus time. And this this third scenario is 1 over A versus time. So again, only in the third try at this do we get the linear outcome, and it must be second order. All depends on your data, all depends on the reaction. Plot it 3 ways and find out.